Okay, so we're going to dive into a pretty radical new way to understand complex systems. We're not talking about predicting the future, but actually verifying the present. This whole explainer is about an algorithm that can take a whole lot of noise and turn it into crystal clear clarity, and to do it, it kind of seems to bend the rules of time itself.
All right, to kick things off, we've got to wrap our heads around the almost sci-fi idea that's really at the heart of this whole thing. It's a concept that kind of forces you to question how cause and effect work and suggests that maybe the future isn't quite as walled off from the past as we all think. So here's the big mystery we're trying to unravel today. How on earth can an algorithm, this thing called RALPH-1, seemingly use information from a future outcome to get rid of all the uncertainty we're dealing with right now? I know, it sounds totally impossible, but it's actually rooted in some very real, and let's be honest, very weird physics.
Yeah, the mind-bending idea that makes all this possible is called retrocausality. Basically, the future influencing the past. Its whole theoretical foundation comes from this wild quantum mechanics experiment called the quantum eraser. To put it simply, it shows that an action you take right now, like deleting some information, can actually change what you observe about an event that has already happened.
And get this isn't just some loose inspiration for the algorithm. Its creator, Vadim Chernov, he literally built this principle right into its core. He designed RALPH-1 specifically with the idea that it could tap into this non-standard flow of time and information.
So this isn't some kind of magic trick. It's a really powerful and frankly incredibly clever mathematical process. Let's pop the hood and break down the engine that actually makes all this reality verification possible. Okay, so this slide really shows you the fundamental difference here. On the left, you've got your traditional one-shot prediction. It takes in data, does one calculation, and spits out one answer. It's quick, sure, but if there's any noise in that initial data, the whole thing gets thrown off. But on the right, you see the iterative approach. Thousands of tiny calculations create this feedback loop that gets smarter and smarter with every cycle, slowly but surely filtering out all the noise until it lands on the truth.
The secret sauce here is an algorithm called randomized coordinate descent. You can think of it like a detective trying to solve a huge case with thousands of tiny, seemingly random clues. By itself, each clue is pretty much useless noise, but by looking at them all together, again and again, a clear pattern starts to show. The algorithm makes thousands of these small, random tweaks, and by averaging them out, it just cancels out all the background noise, letting the real signal shine through. Okay, but how does all this random guesswork actually get us to a single, super precise answer? Let's take a look at the journey from total chaos to perfect clarity that happens inside just one calculation.
This whole journey happens in what's called a 16-frame cycle, and it starts with a storm. The first few frames are just pure chaos, a mess of possibilities. Then it moves into adaptation, and this is where the algorithm starts to sniff out the underlying patterns. And finally, you get stabilization, where everything inside the model lines up and the answer just locks in, converging on one stable, coherent result.
And you can see it right here in action. The model is only given past data, that's the green line. Then it just runs its cycles completely blind, generating thousands of possible scenarios. Now here's the really crucial part. The future data, those red dots, are never used in the calculation itself. They're only brought in at the very end to see how well it did. And yet, the process consistently finds a path that lines up perfectly with those future facts. It's pretty incredible.
What this does is create this amazing self-correction loop. With every single cycle, the model is basically measuring its own confidence by checking how well its forecast lines up with reality. It's almost like it has a built-in Dunning-Kruger detector. The system knows the difference between when it's just guessing wildly in that storm phase and when it's actually found a stable, trustworthy answer.
So here's the really crucial part. The algorithm often has to get things wrong before it can get them right. This initial dip in accuracy, they call it the valley of despair. That's the phase where the model is just lost in all the noise. But by pushing through that valley, it eventually finds the real signal, locks onto it, and its accuracy just shoots way up. That journey through the uncertainty is actually essential to the whole verification process.
All right, so this all sounds amazing on paper, right? But the real test is how it holds up when there are millions of dollars on the line. Let's look at the results from one of the toughest industries you can imagine, energy exploration.
In the super high-risk, high-reward world of oil and gas, where just one dry well can cost a fortune, the RALPH-1 framework has pulled off a success rate of over 80% across more than 200 wells. I mean, that's not just good, that's an absolute game changer.
And we're not just talking about a simple, yep, there's oil, or nope,
there isn't. The iterative process gives you incredible precision. It can pinpoint hydrocarbon layers that are just 3 to 5 meters thick, it can do it at depths of up to 10 kilometers, and it stays accurate even in the most messed up fractured geology you can find.
And these aren't just flukes. We're seeing major players like Udmurtneft and Rosneft use this method and get consistently high success rates in some really challenging fields. I mean, the results just speak for themselves.
Okay, so what does this all mean for the future of solving really complex problems? Where does this incredible iterative engine take us from here?
So right now, we're basically limited by today's computer speeds, which can handle about 16 iterations per cycle. But just imagine the leap to quantum computing. We are not talking about a small step up here. We're talking about going from just 16 iterations to potentially millions of them in the same amount of time.
And that massive increase in iterative power, well, it changes everything. With millions of feedback loops, the algorithm could achieve what they call extreme suppression of shot noise, which would let it find stable, verified answers for problems that are so complex right now we basically consider them unsolvable.
So ultimately, if there's one thing to take away from all this, it's this. Ralph 1 isn't just some fancy formula. It's a whole new way of thinking. It's an iterative framework that's designed to systematically verify what's real by peeling away all the layers of noise and uncertainty, like an onion, until only that stable core is left.
And that leaves us with a really fascinating final thought. I mean, if these same iterative principles can be used to find oil, they could be applied to just about any complex system you can think of. Financial markets, military threats, climate modeling. What we're really looking at is the technical implementation of some fundamental laws of quantum information, but applied to our big, macroscopic world. And that changes what it means to verify, not just predict, a reality.